Hi everyone, I'm Rajat and I'm going to talk about our paper Model Powered Conditional Independence Test. This is joint work with Tirtha, Karthik, Alex and Sanjay. The problem of CI testing is as follows. Given NIID samples from joint distribution of random variables or vectors x, y and z, we need to infer whether x is conditionally independent of y given z. That is, whether the joint distribution factorizes as shown here. We are interested in designing non-parametric conditional independence tests for the case where the random variables are continuous. This is a wide range of applications in causal inference, Bayesian networks, and feature selection. We take a model-powered approach to the problem of conditional independence testing. The idea is to reduce the statistical hypothesis testing problem into a supervised learning problem, and then use powerful supervised learning tools like gradient boosting or deep nets. These tools work well in high dimensions and for real data. In this paper, we reduce the problem of CI testing to binary classification. Suppose we are given 3 NIID samples from the joint distribution. We keep n original samples aside in U1. The remaining 2n samples are processed through our nearest neighbor bootstrap. We show that this generates n samples which are as if coming from FCI, or the conditionally independent distribution. These samples are denoted as U2 prime in the figure. We label the samples in U1 with label 1 and in U2 prime with label 0. The labeled samples are then shuffled and divided into training and test sets. A classifier, which may be a deepnet or gradient boosted tree, is trained on the training set, and the accuracy of the classifier is measured on the test set. The idea is that if f is close to FCI, that is, the data is actually conditionally independent, then the classifier will not be able to differentiate between the two labels, and the risk will be close to 0.5, or that of random guessing. However, if the data is not conditionally independent, then the test risk will be low. Now let's take a closer look at our nearest neighbor bootstrap. In the nearest neighbor bootstrap, the 2n original samples are randomly divided into two groups, U2 and U3, with n samples each. Then the following process is repeated for each sample in U2. Say a sample in U2 is x1, y1, z1. We find the sample x2, y2, z2 in U3 such that z2 is the nearest neighbor of z1 in U3. Then the sample x1, y2, z1 is formed and added to our output dataset U2 prime. We show that the samples in U2 prime are close to samples coming from FCI. The intuition is that when z1 is close to z2, f of y given z1 is similar to f of y given z2 under some smoothness assumptions. Now when z1 is such that f of z1 is high, then z1 and z2 are indeed close. When f of z1 is low, then z1 itself is a rare sample and does not matter much. Here are our key technical contributions. Let phi denote the marginal of one of the samples generated by our nearest neighbor bootstrap. We show that the distribution phi is close to the distribution FCI in variational distance. This is theorem 1 in our paper. However, the samples from the nearest neighbor bootstrap are not IID anymore. We still show that the samples are near IID in a spatial sense, and therefore classification generalization guarantees hold. We prove that the risk of the classifier is close to that of random guessing when the dataset is conditionally independent. We also show that the risk of the classifier is small when the dataset is not conditionally independent, provided the class of classifying functions is rich enough. This is theorem 2 in the paper. This is a GitHub link for our implementation. This is also available as a Python package in pip repositories. We show that our tester outperforms state-of-the-art kernel-based conditional independence testers in real and synthetic experiments. Thank you for listening, and these are the references used in this talk. Thank you.